Okay, so for today we're going to talk about section 1.6, which is logarithmic functions. Like a lot of these things in this first chapter, you may have seen some of these before at some point in algebra, but we're going to give a nice review and kind of go into them a little more in depth here. So log functions, like it says, they're like exponential functions. They're reverses, they're inverses, they're backwards of them. Okay, very similar to somebody having a square root function, and in order to learn a square root function, you have to know what a square is. So it's the same kind of thing here. It's just the opposite direction here of exponentials that we just covered. So going through a few, again, these are just the summary of what we're going to be talking about here. I'm going to go through a number of these lecture slides, not all of them again like last time, because I want to spend more time going over the homework to make sure you're clear on the homework examples here, so you know how to solve the problems that matter. Okay, so a couple different things we're going to have here, dealing with the graphs, dealing with how to use a calculator on a couple problems and all this stuff. So these are at the bottom here, some of the examples that do talk about logs. When you'll see the Richter scale, you see the decibel scale, where they are log functions, so the numbers aren't exactly the same as you normally would imagine they would be comparative to other Richter scale measurements or decibels here. Okay, so one-to-one functions. We've talked about what a function is, where it passes the vertical line test. For every x, there's exactly one y. Couple graphs at the bottom, or on this page here, we have a regular linear line on the left, f of x equals x over 2, and then we have the absolute value of x. And you see the only difference is it bounces back up. That's what the absolute value does. It takes all these points that were down here, and it says, okay, we need to have only positives for the absolute value. So they kind of get flipped upward. So that's why they have these two examples, just to show what they are. Now, in this case here, in the domain, every value corresponds to exactly one value in the range. So if you look at the number 2, x equals 2, at most there's exactly, in this case, 1 point. Over here, same thing, there's exactly 1 point. If you look at -2, there's exactly 1 point. And -2 over here, there's exactly 1 point. So this, again, is sort of the reminder of what it means to be a function. Okay, so in this problem here, they talk about the range value of 2 corresponds. So looking at the first function, let me go with that one. They're talking about the y value. Remember, range is y's, domain's x's. So when they look at the range value of 4 right here, it's like doing the horizontal line test. Going backwards, there's exactly 1 point going the other way. If you look at the number -1, there's exactly 1 point there if we're talking about range values. However, in this absolute value function right here, when I take the number 2, there's actually 2 points. So what it does is it sort of fails, if you want to call it, the horizontal line test. So in a nutshell, here's what we're talking about. Horizontal line test is again a test, just like your vertical line test will tell you if something's a function or not, or it confirms something's not a function. Horizontal line test confirms or denies a special case of functions, these things that are called one-to-one functions. So function needs to have exactly or no more than 1 point for every x. A one-to-one function has at most 1 point for every y value. So it's got to pass the horizontal and the vertical line test. That's what it means when they talk about a one-to-one function. So looking at this graph right here, any continuous function is either increasing or decreasing for all the domain values is 1-to-1. Well, it doesn't matter if it's a line or it's a x cube or something like that. If it keeps going upwards, then you don't get to turn around like the absolute value. So you're going to get exactly 1 point for every y value. Same thing if it decreases for some domain values and increases for the others, that means it's going up, then it's going down, going up, going down. And as soon as you start doing this turnaround, that's when you fail the horizontal line test. That's when you have something that's not a one-to-one function. Now, what that comes into play for is if we start doing inverses of functions, if we have, go back here, if we have a one-to-one function like this, you can do an inverse, which essentially flips your function around, and it's still going to be a function, okay? When you take this one and you try to flip it around, if there was more than one value for any y value, well, when you flip it around, now it's going to have more than one value for some x values, so the result is not going to be a function. It's not going to matter in the end of the world, in the end game here too much if you do or do not have a one-to-one function. It's, like I said, it's for some specific cases for these inverses here. So, talking about what the inverse is. Okay, the inverse is case where you exchange your x's and y's. So every point you have, you flip them around. So if I have an equation that's like this, and I'm just going to go with something very basic to start. This is my function right here. The inverse of that is where you reverse every x and every y. So in the equation, you reverse the x's and the y's. Now, if I was to go and solve this for the new y, you get y equals 1/2 x minus 3/2. These two functions, here's the original, there's the inverse. That's what we have right there. It's a whole different function, okay? Now, what it means, I'll give you an example graphically, because a lot of people like to see this. What does this mean, just by looking at a picture? An inverse, like I said, you switch all the x's and y's. If you think of the line y equals x, the diagonal y equals x, and you take any graph and you flip it around that y equals x, that's what's going to give us, let me use this as a blank page right here, that's going to give us the inverse. Okay, so show you what I mean here. That equation I had a second ago, y equals 2x plus 3. Okay, if you look at this equation, y equals x, just imagine this. Okay, we're taking this function that I just had, and I'll make it a different color just so you can see it. Imagine you fold your paper along this y equals x line right here, and you flip everything around. I'll do my best to draw this. This is the inverse. So you see how everything sort of moves? That becomes over there. Imagine those are the same length. That comes over there. Everything flips around this, and these are all supposed to be exactly the same distances, but here's the inverse of that function. That's what we're talking about when we say inverses. So if you remember the other function we had, I forgot what it was. Something like y equals 1/2 x minus 3/2, I think. That's what this equation was that we found of this inverse function, the flipped over function. That's what an inverse function is. Okay, so why do we get to that? We're going to talk about our log functions. Logs are inverses of exponential functions. Okay, so the first example here we have y equals 2 to x. It increases for all its values in the domain, so therefore it's a one-to-one function. Okay, inverse exists just by flipping around. Remember, you reverse the x and the y. Every x becomes a y, every y becomes an x, and then we solve it by taking the logarithm. We make this into a logarithmic function. Now I'm going to add a lot more detail than what they have here, but this line is important that they have right here. So again, to kind of remind you, if you guys forgot what it means, let's go with something like this. Whenever you see a log like that, okay, I'm just using this example. When you see log base 2 of x, that's how you say it, so we're clear. What they're asking is, just remember this one rule that I tell everybody. A log is always equal to a power. Log equals power. So anytime, I don't care what the context is, if it's by itself like this example, it's part of an equation or whatever the case. Whenever you see a log, it always represents a power. Okay, so the question is, what power can you put on that little number, that base, to give you that number? If you can get that power, in this case 3, then you have the answer to the log. That entire log is equal to 3. It's not equal to log of 3 or log base of 3 or whatever the case. That entire log base 2 of 8 is equal to 3. Because the question they're asking for that is, what do you put on a power of, or what do you put on a base of 2 to get an 8? The power you put on there is a 3. That's what the answer is. So the equivalent form is that right there. These two things say the exact same thing. They're stating the same fact. The top one is in log form, the bottom one is in exponential form, but they're stating the same fact. Now my example is kind of like this right here. We all know the square root of 36. Now if you're trying to ever explain the square root of 36 to somebody for the first time, what you're going to say to them is, well, what number can you square to give me 36, or what number times itself is 36? Working backwards, somebody can say, oh yeah, I got it at 6. That's the answer here. This is very similar, where you have to kind of work backwards to get the answer. You don't have any kind of an operation that you can do to 36 to get 6 without knowing the answer. So you work backwards and say, what can you square? What can you multiply by itself to be 36? Oh, it's a 6. That's the answer to this problem. It's the same thing down here for a log. When I give you a log base 8, or log base 2 of 8, I'm asking, what power can you stick on a 2 to give me an 8? You might have to try a couple numbers around, just like you might have to try a few numbers for the big squares to figure out which number gives you a certain answer. But eventually, you'll realize, oh yeah, it's a power of 3. There's my answer. That's the answer to that log. So that's what's going on when you talk about just basic logs, what they mean. Now you see on the bottom of the left, I have those two equivalent forms. Log base 8 equals 3 and 2 to the third equals 8. They're stating the same fact, just different forms. Same identical equations, different forms. That's what you see here at the last bullet point right now on the screen of this problem. It's saying if you have y equals log base 2 of x, now we're dealing with only variables, you can replace the things. Remember, what this means right here is, what power can you stick on 2 to get me an x? Well, we don't know it, but the answer for now is y. It's this number over here on the left. Same thing. Okay, two equations stating the same thing, therefore the graphs are going to be the same. That's what we have here. That's the basic idea of what these log functions are. Okay, so we have our log functions, we have this, and you see kind of the picture I was trying to show you earlier. I just used lines, but this blue one is our typical log or exponential function. Remember what we talked about last couple days, where it has an extreme side going up or down, it has a flat side going to some asymptote. Well, when you flip this over the y equals x, you take the inverse of it, which is this one right over here. Okay, remember the inverse? You replace the x's and the y's, so we get x equals 2 to the y, and then now I rewrite it in our new form, y equals log base 2 of x. This is how this equation looks right here. So you have to move a couple of traits that we had on an exponential or this one. On an exponential, I told you there's the extreme part that's going either up or down. Well, in a log, you have an extreme part that's going way to the right or the left. Notice there is no asymptote right here. It doesn't stop. It will go on forever and ever and ever. It just is going to go out, but it still continues to go upward. Okay? Then, in an exponential function, remember we had a horizontal asymptote right here? In the log function, you're going to get a vertical asymptote. That's how they're going to translate. That's how they're going to move over. So as you start graphing log functions, just remember, one side's going to go way to the right or the left, but continue to go up or down, and then the other side is going to follow some vertical asymptote. So we have to know what those are. Okay, so we talk about this. A couple rules for logs that you have to keep in mind as you start solving and graphing these problems is that the base can't be 1, and the base has got to be a number bigger than 0. Can't have a 0, you can't have negatives for the base. Okay? Now, other parts that matter here in the logarithm. This equation that they've got right here. All right? The domain has got to also, as in the x, the thing inside right here, this has to be greater than 0. So, sort of like a square root, but a square root can be 0. A log has to be a positive number. It cannot be 0. It cannot be negative. anything inside the log. So later on, you're going to get a problem that may look like this, for example. And if you want to know the domain, you take that inside as it is, and you say that thing's got to be greater than 0. You solve it, and now you have the domain. You can only plug in numbers bigger than -3. But see, you can use a -x as long as it doesn't make the inside be less than 0. That's our big thing that we got to look out for. Okay, now this is going to come in handy because you're going to be plotting points. You're going to be making a table like we did on the last couple sections. So you want to make sure you're picking points that actually work, that don't give you an error when you plug them into your calculator. So you're not wasting time on those. Okay, so what else do we have here? A couple things. There's our kind of see our domain and range on that one. It's going to stop at a certain point. Like in this case, you can tell our domain of the log is everything greater than 0. It never hits 0 because that's our asymptote, but it's going to get closer and closer to 0, but never quite get there. Okay, so a couple exercises. I'm gonna go through these a little quicker, but if you take them and you want to switch them to equivalent exponent form, talked about that earlier. That's your base. Log is equal to a power, and you get that 2 right there. That's your equivalent exponential form. On this first one, take the base, it goes to this number, which is always a power because a log equals a power, and you get the same thing in all of these. Now to clarify, earlier I said you can't have a negative number. You can have a negative number in here, but you can have a log equal to a negative. Logs can't, they're powers. Powers can be negative. You just cannot have a negative on the inside of the log. So just kind of looking at it, and they're going to do the same thing on these slides that I did. So I'm going to skip through this a little faster. Excuse me. Okay. So now we're going to get to some that matter a little bit more. Here we have to go backwards. We have to change from exponential to log, and it's the same thing. You know you're going to have a log, and that little number is the base. Well, here's my base right here. And since you know a log is equal to a power, that's where you put the -2, and the only other number left is the 1/9. That's got to go right there. So once you get the hang of these, you can do this a little bit quicker. I can see log, the base is 2. Logs always equal powers. And it's not so bad when you're first doing these because you're using real numbers, but as time goes on, you're not going to have x's and y's. You're going to have weird numbers that you're not familiar with, so you have to make sure you know exactly where every piece goes when you're doing these problems. What goes where. And there's only 3 numbers, so there's only 3 choices, so you have a good chance of guessing. I just don't want you to guess. I want you to know exactly where everything goes. Okay, so now they want us to solve this. One of our exercises, solve this equation. We have 2 equals log base b of 100. They want you to get the b by itself. Now this is why it's important to know your forms. So I'll kind of remind you, we have y equals log base b of x, or log base b of x equals y. Those are they're the same equation. You know, like 5 equals x or x equals 5. They're the same. Those stating the same thing. They're in different orders. This is your log form, and the equivalent x form is b to the y equals x, or x equals b to the y. And keep in mind, all 4 of these equations are stating the same thing. The exact same thing. So why they come in handy is when you're solving a log or an exponential and you get stuck. You know, I need to solve for a certain letter. I need to get a letter by itself. Well, I can't really get, from what we know so far, there's no way to get b by itself. Okay, because it's down there. There's certain places that are sort of unreachable. But the answer is, if you're ever stuck, go switch forms. Our equation looks just like this one right here. Okay, so switch forms. I take b to the 2 equals 100. Okay, so now our b is a little bit better. It's in a better spot. And then the question is, what number can I put in here? Well, if you really want to solve it, square root both sides, and b can be plus or minus 10 officially. But remember the rule I told you is the base has always got to be something bigger than 0. Therefore, our base is 10. The b is 10. That's how you can solve any of these given functions. So there's a way around them. If you ever see that you're hitting a brick wall or a dead end, go ahead and switch forms and see what we can get. So that's what they did here in the solution. They rewrote this, and then base has got to be a positive number, so you just solve it. Now they just plugged in a number there, but you can actually do the proper algebra like I did and square root both sides. Okay, on this one here, we are doing the same thing. This time we want to solve for x. If you're stuck, switch forms. So they're going to rewrite this in exponential form. Remember, this little 6 is the base of your new exponent. What is your exponent? Well, is it x or is it 5? You know it's 5 because that one rule I told you where log always equals a power. So whatever is the number by itself equal to a log, that's a power. And then we're going to solve x. So x is already by itself. Go figure that out. And 6 to the 5th, we get a 766. Okay, hopefully that's working. Now here's a number of properties, and I'm going to come back to this while we do the homework. Kind of like all the properties you've had, there are ways to get you out or change forms or rewrite something so that maybe it'll open the door for something else. So I'm going to just kind of look at them real quick, and you're going to see you get things like when you get log and a base of the same base right here, they just cancel off, and you get a number 3 here, and you get an x. Same thing if you have a number to a power and the log of the same bases, and then they cancel off and you get this x. Okay, these properties, I'm sure you've seen these before, that if you have a log of two things multiplied, you can rewrite this as the two separate logs where you add them together, or in property 6, you subtract them. Okay, so it's just a refresher of your algebra. Hopefully these aren't too far long gone in your memory and this is coming back to you. Remember, as we do the homework though, I'll explain them a little more in depth, and there's always the videos or the help. If you really have forgotten some of these, you can kind of see the example and they'll walk you through them here. Okay, so we're going to rewrite this expression in a simpler form. So we have log base b of all this. Now if you look at that property 6, if you have a log of one thing divided by another, you can write it as 2 logs subtracted. Then if you have a multiplication, you can rewrite those as 2 things added. So how they do this one right here is they rewrite it first as this log, the top, minus the stuff on the bottom. Then they rewrite this one as a log x and a log y. Here it's a log t and a log z, but just remember they're both negative because of this log, so that's why they use the parenthesis here. So the question that some of you may be asking is, why would we want to write this log into all of these logs right here? Well, there's sometimes when you're trying to work out an equation, you don't want that to be a complicated log inside. You want to have nice simple logs. So these properties break it down where you have it's like a pro and a con. You can have a bunch of logs that are simpler, or one log in this case, and it's a little more complicated of a log. And it depends on the context of your problem. Okay, now this one, go back to your properties. Property number 7. When you have a power on something that you're taking a log of, you can actually move the power up to the front. And that's a unique one, and it really does save you a lot of trouble. So we can take this 4, we could bring it up. Okay, just like they did right here. See that 4 comes right to the front. Everything else of the log stays the same. Then they can break this down into 2 different pieces, and then we can distribute the 4 and have this. Okay, so whenever they say simpler form, it doesn't look simpler to a lot of you, but it means a simpler inside. Think of it that way. Whenever you're talking about logs and they say simplify or write in a simpler form, it means they want to have more logs, but inside is a lot less complicated. Okay, same thing here. Let's see if we can write this in a simpler form. Now, if you remember that property that says if you have a base here, and you have a log 3, they can cancel. The problem is, and I'm going to go back, that's this property right here. The difference is there's no number in front of the log like we had. Okay, we got to get rid of that number. So this x kind of screws things up. I can fix that by applying that same property we did just now. We'll take that little x and we can bring it out from in front, and it's now on the b. So now I have a 3 and a log 3, and now those will cancel, and I'm left with just bx, and that's the simplified form. That's it. Another one right here. Now we start getting a little more complicated equations. And notice, go back again to these properties. These properties are dual directional. Okay, they go both directions. So sometimes you have this log of m over n, and you want to rewrite it into 2 logs of m minus n like this. Or sometimes you've got 2 logs and you want to shove them together into 1 log. On property 7, sometimes you want to take that power and put it out in front. Sometimes you have that power or that number in front and you want to move it to the back and make it a power. It depends on what you're trying to solve, what you're trying to get. So in this case, we have 2 logs. Now the first rule is they have to have the same base to combine them, and they do. So I combine them, and I was going to go one step at a time, but here it goes. So we combine these. So the rule is if you're adding 2 logs, you multiply the insides together. Now it's 1 log. Okay, then they just do a little foiling here, and we still have log base 4. We have x squared minus 36. Now if you look at this step right here, from here to here, what's happened, it's not always an easy property to see, but this is a case where they switched forms. We were in log form right here. Now we're in exponential form. You see how you took that 4 and you brought it to a power of 3, and then that equaled everything on the inside. And now at this point, this one should look like a normal equation to solve. You can bring this over and square root both sides, or you can even bring the 64 over and then factor. That's more of the algebraic way. Either way, you're getting 10 and negative 10. Okay? Now, we're not quite done. The one thing when you solve an equation is you get your answers, but you need to go and you need to check your answers. Now, I don't mean checking like in the old way where you got to check and go verify everything. I mean this. Excuse me. Take that 10, go back to the original problem, and plug it into both logs. And all I'm looking for is, excuse me, I want to make sure that number doesn't make any logs be negatives. So when you plug a 10 into this first one, sorry, you get a 16. I don't need to go any further. I just know that's a positive number. That's good. When you plug a 10 into here, you get a 4. Again, that's a positive number. That's good. 10 is a solution. Now I got to go plug the negative 10 in there. When I plug a negative 10 into the first log, that gives me, a negative 4. That's a problem because we cannot take a log of a negative number. Negative 10 is not in my domain. That means I have to throw it out. There's actually only one solution here. So you have to do that one final check of, you go through this entire process. Then when you get your answer, just make sure it doesn't ruin anything in the original. You always go back to the original equation, not one of these second, third, fourth steps, but the original equation, just to make sure it doesn't cause you to have a negative inside of a log. So that's what they explain here on this final paragraph here. Can't have a negative inside of a log in the domain. That's why when you plug in negative 10, it breaks that, so negative 10 has to be thrown out. So they tell you of all the possible log bases, E and 10 are the most common ones used. Couple things here. And then when you have a base of E, this is kind of a weird one. I'm going to show it here. Yeah. When you get a log base E like this, all right. Again, let me write this. If I give you something like 20, what they're asking, same question is, what power can you put on the E to get you a 20? Now the difference here is, if I had a log base 10 of x equals 100, what power can I put on a 10 to get 100? You can kind of play around a little bit, and eventually you're going to see a 2. You're going to get that answer, okay? Oh, I did that wrong, sorry. Do this one more time. This is what I was trying to ask you. Log base 10 of 100. The question is, what power can you put on a 10 to give you 100? The answer is 2, and you play around with it, you're going to get it. For these E's, you can try all day. You're never going to get these because they're going to be complicated decimals because E is a forever decimal. So it's going to be difficult to find. Same thing when you're dealing with a log base 10 of something that you don't know. Okay, what power can I put on 10 to give me a 237? All right, so I'll show you a couple things. 10 to the first is 10. 10 to the second is 100. 10 to the third is 1,000. Notice we're not ever going to get 237, but what I do know is 237 is right there in between 10 and 100. So my answer is going to be somewhere there. I don't know what the answer is, but I know it's going to be somewhere between 2 and 3. 2 point something is what I know. And I can do that without a calculator, just knowing that it's got to be in between these two because of what I know. E, you could try to do that, but it's going to take even longer. But what's nice is there are buttons we can use on our calculator. Anytime you see a log base 10 of something, number one, they're going to write it as just log 10, log x, I'm sorry. They don't show the base. When there's no base, it's assumed it means a 10. Just like when you see an x, you don't put a 1x in front of it, it's assumed there's a 1. Or a power, if there's no power, you assume the power is a 1. If you see no base on a log, it's assumed it's a log. And you have a button on your calculator where you can find this. Show you what I'm talking about here. Let's see. Excuse me. So remember that 237? There's a log right here. Some calculators, it's just plain log. I type in 100 and I hit that log button. It tells me the power. Log of 100, which I showed a second ago, is 2. And I talked about we can't do 237, but I can hit the log button and you see I get 2.374. That's the power that you put on 10 to give you 237. All right, it just happens to be a 2.37. Don't think it's always going to be that way. But if I was to say, hey, give me the log of 789, it's 2.89. Something, up there, getting close to 3. So you can hit that for anything base 10. Log of E, I'll write this over here. When you see a log of E of 20, it's known as a natural log, this ln. Okay, again, no base, but you assume whenever you see ln, it means natural log, it means log base E. There's also a button right here. So if I want to find natural log base E of 20, natural log of 20, I hit the 20, I hit that button, it's 2.99. And what that's saying is, if I took E to the 2.99, I'll call it 996, that's going to give me 20. Or E is 2.7 to the 2.996. Never going to be perfect, but it's going to give you 20. But they're asking what's the power you can put on there. This is how you can use your calculator to find those different things. Okay? So let's resume where we were. Okay. So there's your calculator, your 2 buttons. And now they want us to find the exact solution in terms of E. So let me make this clear too. Whenever they ask for an exact solution, it means no calculator. Don't give me decimals, don't round, because all calculators are going to round. Even if you go 8 decimal places, you're still rounding something off. You're shaving off something or rounding up or rounding down. When they want an exact, that means they want you to do it algebraically. They want you to do it with the formulas. So see how this is done. When we're trying to solve for x, let's first try to combine those natural logs, those logs. So remember, all those properties I gave you earlier, they apply for natural logs as well. Any log they apply for. So here I have 2 natural logs. It's a subtraction, so it becomes a natural log of x plus 1 over x. Okay, now the part that you don't see here in this step, right from down here, this is the same as log base E. Remember, that's what natural log means. So this is in log form. I'm going to switch this to exponential form, which means take my base, bring it to this power over here, and that's going to equal all the stuff on the inside. That's how they got this line right here. Okay, so then they move the E to the first is just plain E. So then they multiply both sides by x. You get x plus 1 equals xe. Then they put the x's on one side. Now this part right here, why we do this is we're trying to solve for x. So if you look at all your terms, I have an x, I have a 1, I have an xe. All your terms that have an x, put those on one side. All your numbers or non-x's, put on the other side. So they move over the xe, they move over the 1, then they make everybody a positive. They switch the signs, that's fine. And then we factor out the x right here. and then we divide by that thing that we just factored the x out of, and that's how we get our final solution there. And that's what they mean by an exact solution. Not plugging this stuff into a calculator, but going and isolating that x using all these properties, using the algebra. Now, like I said, at some point, I know you've seen this stuff in algebra before. I'm hoping that this was just a nice refresher and it's not brand new to you, but again, you can always expand on, look at the other videos or watch the PowerPoints a little bit more, and you can kind of see, what more I'm doing if any of this is not quite ringing a bell. Okay, so we talk about the keys here. Did that already. So here's just a nice little thing. If you want to play around with this, you can always pause the video and try this out here. This is just plugging in numbers to your calculator to confirm what they come out with. And remember, on this first one, when I'm asking for log of 5287, that's the same as log of 5287. And when I plug that into a calculator, it's telling me this power. It's telling me the power that I can put on a 10 to get 5287. So that's what it means when you plug in a log. And I wanted to make sure to go over that because when you learn logs, I can bet that most people don't really learn exactly what it means. You learn all the rules and the properties, but you don't kind of get the big picture. You just kind of go along, and that's why people forget it. Log always represents a power. Log always equals a power, and specifically it's a power you put on the base to get some value. So on that part B, natural log means base E. What power can you put on an E to get you 0.0000124? Okay? And then if you plug this into a graphing calculator, which we're going to use in a bit for other problems, you see they give you the same answer, or you use the regular scientific calculator that I just showed. And on that last one, if you try to plug in log, if you remember I told you the rule, you can't have a log of a negative number. You can't have a log of a 0. So that doesn't exist. Try plugging into your calculator and you see you're going to get an error. Whether you use a graphing calculator or Desmos or you use the scientific one I just showed, they're all going to tell you the same thing. Okay. Now we solve it using a calculator, and you'll see log of x. We need to get this x by itself. Still got to do some algebra, then we'll use a calculator. And they tell you we want to write this in exponential form. Right now it's in log form. So if you've got an x and a log, you can't really get it by itself. But if you switch to exponential form, you see what happens. Now we will. So make sure you see how I got that. Okay, log. The previous line right here, that means log of base 10, even though we don't write it. And I'll say again, you can have a log of a negative number inside, but you can have a log equal to a negative. So to switch to exponential form, we take the base, that little 10, we bring it to the power, which is what the log is equal to. And that's going to be then equal to whatever is inside the log. That's our rule of switching from log form to exponential form. And then you have the x by itself. Now you just plug that into your calculator. And again, I'll go back to my scientific calculator, which everybody, if you don't have a graphing or you don't have Desmos, you can do this. There's this button right here. It's 10 to the x. It's kind of like we did before. You type in the power. Make sure you hit that negative, and then whenever you hit this button, it takes 10 to that number, and that's how we get the 0.013677. Okay, that's where they're getting that from. Okay, and then they round it, and this is another way do I use a calculator and get the decimal, or do I go solve like that last problem? Well, if it says exact answer, you want to see all fractions, no decimals, keep it precise with the e's. If you see something like round to the nearest or 4 decimal places, whatever, that's your kind of go ahead to use the calculator, and it told you to use a calculator. So here we do the same thing. It's in exponential form, but remember that means log base e of x. That right here. It means log base e of x. And I say that so that you remember when we go to the next step of making this into an exponential equation, you take that little base that you didn't see, which is an e, and you bring it to the power of what the log is equal to, 3.416. That equals the inside of the log. And then There's also a button on your calculator for e to the x, which we talked about last time. You plug in the 3.416, hit that e to the x button, and you get the 30 that you see right here. Okay, so a couple more, then I want to get to the homework. In this case right here, when you have something you're trying to solve, it's in exponential form, so you can move this to log form right now, or you can take a common logarithm of both sides. You can take the log of both sides, and it's doing the same thing. You can take the log of both sides, you can take a power of both sides. As long as you do the same thing to both sides, we take the log of both sides, and then if you remember, when you have a log base 10 of 10, they just cancel out and you get just an x. And you would have gotten the same thing if you took this equation right here and you switch it to log form. Again, I'll tell you that same thing. Remember, you take a log, the base is that old base, log equals a power, the power right here is x, and then the last number, the only place to put that 15 is right inside there, and we get the same thing, notice, right there. So either way, you can take the log of both sides or you can switch forms. Why I always emphasize the switching forms is it gets you out of a lot of jams. It gets you into a better situation more times than not. It's the same thing right here. Now, in this case, I can switch the forms. I can take the natural logarithm. I can take a log base 5 of both sides. Now in this one, this is actually good. When you don't have a base that's a 10 or an e, this is actually a good property here. We take the natural log of both sides. So you see we had this equation right here. They just put an ln in front of both sides. As long as it's in front of both sides, not every term, but the entire left side and the entire right side. And then now, see if you figure out what they did here is they got that x and they put it out front. That was that other property. That property 7 they listed on that earlier slide, where if you have a power on the x, you can move that right out in front. And then now we divide both sides by natural log 5 to get the x by itself. And you can plug this into a graphing calculator, into a regular calculator, whatever the case. But again, it's important you learn how to use whatever calculator you have so that the tests, you're not figuring it out on that moment, or on the quiz, I should say. So that's what a lot of this homework is. It's going to get you comfortable with the mechanism that you're using. Okay, so a couple other things here. They're just rewriting some properties and showing some facts. Now, what this is, this whole thing, this is proof of another formula, is that whenever you have this, you can rewrite it as this. This is called the change of base formula. What it is if I was to give you log base 10 of 752, you can go plug that into your calculator. If I told you natural log of 752, you can plug that into your calculator. If I told you log base 4 of 752, unfortunately, we don't have a base 4 button on all the calculators. Some do, but a lot of them don't. The fix is, if you look at what we have, this is the same thing that I have circled up here. If you have any base, any log of it, you can rewrite it as a new base. So I can rechange this as log base 10 of 752 over log base 10 of 4. It's like the old base gets moved in there. Or I can make it natural log of 752 over natural log of 4. I can change it to any base I want as long as it's the same base on top and bottom. But why we do this is now we have both these buttons on our calculator. We have natural log. We have log of base 10. So this just allows us to now calculate any base. No matter what problem they give you, you can change the base and you can get it to one that you're familiar with, a natural log or a log, and you can use your calculator. Okay, now we get to some word problems here, and we're going to see some more of those on homework, so we'll cover a couple here and then we'll get to the homework. So the doubling time for an exponential growth model is the length of time it takes to give value to double, or given value to double. Kind of like that half-life of the radioactive decay we had last time, or interest rate, we're trying to get to a certain value of an investment. It's the same thing here, except we're trying to see how long it will take to double. Now, of course, nothing's guaranteed, but we're just going by what we have, what the past data has shown. Okay, so a couple things here. Logarithms are going to help you figure these out. How long to the nearest year will take money to double if it's invested at 15% compounded annually. So remember this formula that we used the other day. All right, formula that if you don't know by heart, it's okay. You just got to have it close by. Have it handy when you're on taking your quiz. I would even suggest starting a separate sheet of paper where you have all of your properties, like the 8 properties we had today, along with some of these formulas, just to have as quick reference so you don't have to go digging through a book when you're taking a quiz or the final. So in this case, use the compound interest formula. They give you that right there. They tell you the rate, they tell you the M, they tell you the A. Now you see how the A is 2P? Because the P is your principal, your initial, your starting amount. We want to know how long it's going to take to double it. And the good news is it doesn't matter what the value is. If P was 100, we want to get to 200. If P was 1,000, we want to get to 2,000. It's just double. The P is irrelevant. And you'll see here in this first step. Okay, stop there and let you see what they did. First thing they did was they divided both sides by P and it canceled out the P. It doesn't matter what it is. We just care about that 2 on the left. Then they combine in the parentheses the 1.15. And now you see we have an equation where we just want to solve for t, and we're going to use the properties that we learned today. How do you get that by itself? Well, it's an exponential form. I can get it into log form, or the easiest way is log both sides. Now, a lot of mathematicians, as you see here, they're going to use natural log of both sides. Sometimes when you're first learning this, you don't like that natural log, so you can just do log of both sides. If you were to take that equation and write it as log of 2 equals log of 1.15 to the t, you're going to get the same answer. It may look different along the way, but it's going to be the same thing. You see, I'll kind of do this parallel, bring the t out front, and now we're going to divide both sides by the log, and this right here is what is going to be equal to t. That's what I plug into my calculator. So whether you plug this into your calculator or you plug this in, they're both going to get you the same thing, which is 4.9595. Rounded up, it's the nearest year is 5 years. That's at that interest rate, it'll take about 5 years for this to happen. Okay? All right. Now our last one is this thing called logarithmic regression. And this one requires a graphing calculator or Desmos, and we're going to do that with a homework problem so you can see exactly how it works if you don't have a graphing calculator. If you do, go ahead and use it. If not, you're going to have to go to a website, and the easiest one, like I feel, is Desmos, but most graphing calculators will have this. So what's going to happen is you're going to plot a set of data. And this is one of the most real-life problems you're going to have. You know, if you're working for a company and you're trying to predict whether it's sales or costs or, you know, how many you can produce, whatever the case, you have data that's given. And I remember data is just a prediction of what's going to be in the future. Nobody knows for sure, but if it holds, that's the model that we're going to try to show. So what happens is you're going to go into your graphing calculator or Desmos, you're going to plug in your data, and then you're going to plug in this little equation right here, this y equals a plus b ln x. And what that's doing is that's saying, go find me the log equation that makes this true. So, you know, there's a stats process, this linear regression, LNREG, will go and analyze the data. It's going to figure out an equation, and it's going to spit out this equation right here. So it may not show the equation, but notice what it does is if you plug in this equation right here, it tells you what the a value is. So you replace a with the 256. It tells you what the b is, negative 24. You put it in here, and now you have an equation of x and y. And so now if you want to know what you think it's going to be at 6,000, 7,000, 25,000, you plug it in for x, and then you're going to figure out what this other value is here in the second column. So that's what it's going to be doing. So this is what they do. They found the equation, then they plugged in 6,000. Use your calculator, and you get this $47. In this case, it was a cost. So that's how that one works. Like I said, let's get into the homework, and you can see exactly what I'm talking about. So at this point, now my course is going to start to look a lot different from yours soon. You know, get in your course, go to your assignments, and you'll see all these different ones. And you see things are starting to pop up every week or every few days. More and more these are going to pop up. We are at the point of about to finish, homework number 2 right here. We finish homework number 2, 1, 3, 1, 4, 1, 5. Your quiz is due on Monday, so make sure that's done Monday night. Now this, what I'm going over, is the first section of homework number 3, the 3rd week. All right? So homework 4 is already up there. Don't feel you have to get in there right now. That's just there in case people are ahead. I'm giving the option, but I don't open them all up because I don't want to overwhelm anybody. So you'll see homework number 3, and I'm going to do every few of these here. Okay, so let's look at this here. Okay. All right, so starting number 3. Write the equation in equivalent log form. All right, so I'll write this up here again. We have x equals by is the same as y equals log base b of x. That's your little special formula that you should have written down somewhere that switches your forms from log form to exponential form. Now, what I did again is I'm just writing these backwards. You don't need all of these. It's just a way to show you that any of these 4 are all the same. It's not the top equals the top. Any of these are equal. Even going up and down, they're all the same equations here, okay? So what we have is this one right here. What you have to identify is, well, what's my power? What form am I in? And you can see clearly we're in exponential form because there's no log there. Okay, so to rewrite this as a log, we got to find the base. Well, the base of the power is the same number that's going to be the base here. And then remember my rule. Log equals power. So put the 1/2 over here. That's what's equal to the log. And the only other number left is this 2. It's got to go inside the log. So that's the equivalent log form they want. You can do log base 4. And I think if I just, okay, I got to hit this button. So you're learning about this, that button right there. That's going to give you the little subscript where the power is. And now I hit the 2, hit the equals 1/2. And we're good. That's all it is. Okay? So a lot of these first couple of problems are just getting you used to formatting and rewriting them, and they're good problems because they get you comfortable with these properties. We have a lot of properties that we're doing, so you have to know how to work these. This one, now again, notice without a calculator means make sure you don't go give me decimals here. They want a precise answer. Generally, it's going to have a fraction or a root or an e or whatever. Okay, so we have log base 2 of x equals 2. They want us to find x, solve for x. Well, when x is in a log, we can't do anything about it. Hence, we have our little formulas up top that we can switch. Let's try taking this out of log form and moving it into exponential. Well, there's my base. Log equals a power of 2. And guess what? We already have it solved. It's literally that fast in some of these problems. And there it is. So like I said, you're going to get a lot of these where the initial, the answer is actually not going to be a ton of work. You just have to make sure you look and see how to do it. Make sure you're comfortable and familiar with this process because this is going to get more complicated. So I want to make sure you can see these. All right, now we start getting to one of these that I was talking about. We have log base b of x plus log base b of x minus 3 equals log base b of 18. Okay? Now, first thing I want you to see, you can't just get rid of all the log base b's. Like, I don't write this at all, but I see a lot of people do this on a test. That doesn't happen. You can't just get rid of the logs. Now, if you had one log equal to one log, then yes, you can do that. But when you have multiple logs, no. So the fix is, we want to use our property and let's combine these. And remember the rule. If you have the same base and you're adding them, you can write them as a single log that's being multiplied together. Now, because you have one log equals one log, you can cancel the logs and you only have the things inside. So that's when you can cancel both sides, not in the first step. So at this point, I'm just going to solve, and I'm going to bring the 18 over. And once again, our favorite rule, our favorite process, factoring. I get x equals 6, x equals negative 3. Now I'm going to do something on purpose. I'm going to get this wrong. Put 6 and negative 3 in my answers. And you notice when I check it, it says that's not correct. Okay, why? You guys remember, we talked about this earlier. When you solve a logarithm, or you solve for x and it was a log problem, you have to go take this and go plug it into the original logs just to make sure you're okay. Now on the right side, there is no log, there's no variable in the log, so I don't have to worry about the 18. But anywhere a log has an x and you solve for x, you have to plug it in to make sure it does not give you a negative number or a 0 inside. So when I plug in the 6 right here, I get a 6, that's fine. I plug it in here, I get a 3, that's fine. So definitely 6 is going to be a solution. But when I plug in negative 3 to this first one, that log gives me negative 3. I don't need to check anymore. So if one log, there could be 8 logs and 7 of them are good. If one log gives you a negative or a 0, you can't use that answer. So my only solution here is going to be a 6. And hopefully that's right. But that was why we got it wrong the first time. If you try to plug in a negative, and it doesn't mean all negative x's fail, by the way. You have to plug them in up here to see. Because you may have a log that's x plus 13. Okay, just making that up. If you had it and you plugged in the negative 3, that would be fine because it gives you a 10 inside. It's what do you get after you plug in the x, not a simple case of is the x negative or not. Don't just throw it out because it's negative. You have to check everything. And then on the other hand, it also means just because you have a positive x, you can't always use every positive x. You have to plug them into the original to see what you get. Okay, so let's go through, let's get to number 15. Continuing my trend, I'm just doing, like I said, every 4 or so, just to give you a sample of these, just because we don't have, I don't want to give you a 3-hour video every time. But like always, if there's a problem that I've skipped and you feel like I really could have used that one, not a problem. We can talk about that. We can see, I can work with you individually if you have a question. So solve the equation to 4 decimal places. We have e to the x equals 5.548. Okay, so on this one, my process is I can switch forms or I can just take the natural log of both sides. And that's because I see an e there. And then the property says if you have a natural log of e, you can just go and cancel those out because it's the same base as what you're taking the natural log of. So natural log of 5.48, go get your calculator out. And 5.548, hit the natural log, and we get 1.7134. And then remember, always look at what they tell you to round it to. Sometimes people give too much. On a real exam, I would take it if you went further, but if it's on this computer-graded exam, they want to be very specific. Make sure round to 4 decimal places, and we have our answer. Okay? Let's do a couple more here and see what we get. Now, these ones I went through here, they're just graphs, same as we did in the last chapter. Just kind of plot a few points, see where they land, and you're going to eliminate 1 or 2 immediately. Then you keep plotting a few more points, you're going to eliminate another one as well. Okay, so the table shows a yield in bushels per acre and the total production in millions of bushels for corn in a country for selected years since 1950. X represents the years since 1900, so that's why you see the X is 50, 60, 70 on this table on the right because it's talking about how many years after. So 1950 is 50, 2010 is 110. Now they want you to find a logarithmic regression model for this, and they give you the equation to use. So what I want to show you is, if you have a calculator, you can do that. If you're on Desmos, like we have right here, I'll show you where we go. Okay, so you go into your graphing calculator. You want to go into these tools. No, not the tools, sorry. Oh, that's, where did it go? Okay, I had it a minute ago. I lost where I was going. Okay, the plus, that's what it is. Okay, the plus, hit the table. Missing the one important thing here. So go into your picture here. You want to enter the data that you have. Okay, so get used to this. As long as it's a return. If you do a tab, it goes left, and I can type in my 36. And then if I hit return, it goes down. So sometimes I like to just type all the X's in first. And sometimes, depending on what you're with, it'll kind of predict. I didn't type these. Once I started doing the first few, they realized it was going by tens. These now, I'm just going to type them all in. And you're making a data table. And you'll see it's going to plot the data that you have. Okay, so you may not see much here. Got to zoom out a little bit. And you see, here's my points. Now, it's real life. Okay, so it doesn't always follow a linear, a line, or a parabola, or a cube, or even, in this case, a natural log function, but we're going to try to find the best possible one that fits this. So this is the weird part here. You see this equation, they tell you the logarithmic regression model, y equals a plus b natural log x, in decimals at least. You're going to type this, but instead of y, you got to type a y1, a y sub 1, okay? So, and then when I type that on my keyboard, I'm just literally going Y1, and it automatically knows to do that. And instead of equals, I'm going to hit this button to the left of the 1. It's this little, like a tilde. You know, in some languages, it's got that, you know, a little swish right above. It's to the left of the 1, so it's shift that key to put this up here. Then we just type in this exact equation that you see above here in the problem. A plus B x, natural log x, and then don't forget you got to do an also first right there. And what it does is decimals will find the closest best natural log function that fits around these. And you see, if we zoom in here, it's not hitting my dots exactly because, again, these are, you know, actual real data, so they're not always going to follow a perfect pattern. But you see, they found the closest possible logarithmic equation to it. And here's the good part. It tells you the AB right here. So when I go in this model, the first one is A, I type in this negative 518.4, and it says round to the nearest 1 decimal place, so I'll put the 5 in there. And then in this other one, it's the B, the 140 point. Now when you round up, it goes to 96, so we're going to have to make this a 141, 141.0. And there's our answer. Now they want you to find the estimated yield in 2022. So remember, 2022 is 122 years past. You can do this, or you can say x equals 122 just to get the exact point right there. And you can see it's 158.7. And, oh, did I miss that? Oh, go back. I'm sorry, I did something wrong. You guys see what I did wrong on that one? It's not 122. It's the years after 50. So I actually got to put 72 in here. Important to read it. And where does 72 hit? 84.4, I believe. Okay, something didn't look right here. Make sure my data is all good. No, it is after 1900. What did I get wrong? Did I put 112 and not 122? Okay, go back. 122 is what I should have had. 2022. Huh. Okay, so I think I'm overthinking here. I was right the first time, the 2022. I had another problem earlier with another class where we started at year 50, and that was where the addition came in. So from 1900, it is 122 years. That's good, 158.726, and I see my mistake now, I think. They want us to round to the nearest integer. Kind of tricked me there. Let's try the 159. And there we go. Okay, so play around with this. You'll see this Desmos is a nice, powerful tool. And like I said, this is what we use in real life. We're in some sort of a production, anything with data here, and you can use this to try to figure out what will it be. You know, if we want to go out into the year, 200 years from there, 2100. Now it's way up there. They're going to predict it's 228 if you follow this model. In real life, as you get more data, this red, this approximated linear regression, this y equals natural log function, it will alter. It'll change as other data comes in because maybe there are new factors. COVID, for example, changes some factors. So this might change a lot of models, but you can kind of go with it and see what happens. So this is how it is. I'll stop right there for this one. I'll record some other videos for section 2, 1, and 2 and get those out in the next day or so. But this should get you through the first 24 problems or so of the homework. And if you have any questions, let me know. And that's it for this time.